Hi everyone. I said in class on Wednesday that I would make some videos about how to use fun and fix, and I'm finally getting around to it. I'm sorry I've been so slow. Better late than never. Let's start here. Take a look at a list of numbers, return a list of those numbers plus 1. At this point, I hope that for you it would be a more or less trivial exercise for me to say, well, write this function however you want, right? Writing it as a little recursive function should be quite easy for you, right? It's just almost typing more than anything. Right, and you have your choice of things that could go here. Maybe you write s of n if you like. Maybe you do 1 plus n. I'm not really that concerned about it, right? But all this should be relatively simple for you. If that definition didn't spring out of your fingertips, if you really weren't sure how you would start, you should talk to me because this is sort of the kind of function that I expect to be relatively easy for you at this point. So let's test it real quick. 3216, okay, looks good to me. All right. Now, suppose I said, write this using map or filter, right? And I want you to think of this, if you're sort of resistant to using map and filter, think of this like a form, like a kata in martial arts, right? The point is not that it's necessarily better for you to write it that way. I don't know. It depends on a lot of sort of circumstantial things, whether writing it with the fixed point like we see here or writing it using map is better. But for the purpose of this course, your ability to write it with map to me is a measure of how comfortable you are with the abstractions that we're building. So for that reason, I'd really like you to be able to do it, right? I want you to feel really comfortable. So let's look at a couple different ways that could go. So let's look at the map function first. So I've written at here so we don't get that funny like question mark x thing. Okay, so given a function of type x arrow y, we take a list x to a list y. Okay, so in this case, x and y are the same. They're both nats. We need a function that adds 1. So there's a couple of different ways we could do this. Prime, great. So I'm not even going to bother writing the type here. I'm just going to say, well, this could be map fun n plus 1. Okay, interesting. What's going on there? Well, maybe it'll be a little clear if I do this. That's the same. This is a good starting spot. Here's another way to do it, right? I could just do this. It's another definition. Maybe you want to write the function differently. Maybe you want to say this. You gotta give it a fresh name. Or maybe you want to say this. All of these are good definitions, pros and cons. I think that, you know, this is probably the clearest. This is certainly far and away the shortest. Right? So it kind of depends which of these would be good. But hopefully each of these makes sense to you. What about add 2 each? So I'm not even going to bother writing down the fixed point. What might it look like here? Well, here's a little pro tip. You can take this, paste it, and for all of these, I can just replace 1 with 2, except for this one. Right, this one doesn't quite scale up in the same way. What would it look like if we wanted to use s? Well, it might look something like this. Right, but this one is no good. Okay, let's keep going. Take in a pair of predicates, excuse me, and a list. Return those elements that pass both predicates. So let's do the recursive one just to see what it looks like. P1, P2 are x arrow bool. Okay, we need to take in the type x implicitly. Whoops. And L is a list of x's, and then we'll get back out a list of x's. Okay, what's this going to look like? So match L with, if there's nothing, then there's nothing. Otherwise, what do we have? Well, if P1 of x and P2 of x both hold, then x otherwise. Okay, so I've done some fancy alignment here. I've used an if and some logical control flow. You might have been tempted to write this in a more complicated way where you test P1 in an if, and then in the then branch you test P2, and that's really what an AND is for. So going forward, I think we should spend a lot more time making sure we write nice, concise conditions and stuff like that. Let's test this function. So what's a good thing to test it with? Well, okay, let's test. We want odd numbers that are less than or equal to 47. Okay, but we need a sample list of odd numbers. But we have conveniently a function that we've already written that builds lists for us, right? So we don't have to write it down concretely. So this is actually really nice. Once you've written functions like 0 to n, it's super convenient to be able to use them to test your code. So here we can see down at the bottom, this looks like all of the odd numbers from 1 through 47. Success. Okay, let's write some other versions of this. So it'd be nice to do this using filter. So filter is sort of, I think, the most appropriate thing to do here. So let's try one version. One thing you could do is you could say, okay, well, filter the things that pass P1 from L. And then once we've seen those, oh, we probably need to take P1 and P2. Whoops, wow, screwing the pooch on the type here. Okay, oof. Okay, so this will be the list of things that pass P1. And then we'll just say, okay, look, out of those, find the things that pass P2. Let's run our test. Okay, looks good. This is nice. This is a good solution. Feels pretty clear. Now, we could probably do better. So maybe you care a lot about efficiency. I don't particularly right now, but it's nice to think about. This goes through the list once, and this goes through it again. What if we only went through once? Well, then we'd have to pass a different function. We'd have to be a little more clever, right? Switching P2 and P1 here isn't going to save us much. So we just need to be a little more careful. So we could say let our new predicate, our new tester or whatever, test x be P1 and P2 x. Oops. P1x and P2x. So that needs to be a colon equals. And you got to give it a fresh name, right? And this works too. We've defined a little function test right here that says, well, the things that pass test, if we write the types in, maybe this will be a little clearer. It's those things that pass both P1 and P2. So this works also. This is a nice way to do it. I don't like this quite as much. Feels a little verbose. I would rather write it this way. I keep messing up the names. It's just also looks good. This one to me seems like the best one. Now, you could choose to write a little type annotation here if you want. It's really not that big of a deal. A thing I want to note here is that what we've done is now we've wrapped the function. We're doing this post-processing on what the function does. And this is exactly the sort of work that you'll needed to have done in even GT7. It's the kind of work that you'll need to do this kind of wrapping is a good way to implement partition, right? All of that is really nice. Okay, so far we've used map and filter. Here's a function that's going to want us to use something a little fancier. We kind of need to do both mapping and filter. Take in a list of numbers, return a list of half of the even ones. Okay, so you could write this as a fixed point. Have evens. L is a list of nats. We're going to get back a list of nats. We'll look at L. Hey, if it's empty, we're done. Kind of a pattern here. Otherwise, what are we going to do? If n is even, and keep going. Otherwise, so a neat thing that just happened there is I used alignment to catch a typo. It's kind of cool. Right, so this should get us the list 1, 2, 3, 4, 5. Beautiful. Okay, so that's fine. This is a function that I would expect you all to be able to write with relative ease. Um, which higher order function do we want to use? Well, it's kind of, if you look back up, like the the structure here is generally a map. We're doing something to every element, but we have this if here, which is a little bit like a filter. So we want something that's a combination of map and filter. So a first approximation would be like, well, just use both those functions. Okay, so filter out the evens from L, and then map half. Let's see if it works. Stunning. Okay, that's nice. This again has this like the double filter we saw before. This I think is actually very very clear. And fancy functional programming language compilers will actually combine these into a single loop, which is pretty cool. It's something that Haskell will do, for example. But maybe you'd rather do it in one go. So functions like map option are sort of like have your back here. Right. Map option says, well, the function f that we'll be mapping over the list returns an optional y, a none or a sum. And if you get a none out, that means we'll drop the element. So we can use this to kind of build the test in. So here's how another way to do it. Here's I think maybe the nicest solution. Okay, well, let's start one way. So we'll say let you know, our haver of n a nat be if even bn, then half n, else none. Let's leave that in and see what error we get. And now I'll say something like map option haver over L. And then Cox says, what? None has type option A. Well, expect to have type nat. Oh, that's weird. So something's wrong here. So let's just option nat. Ah, now we find out where the real problem is. I forgot a sum. This is a problem I've noticed many students having. We're not working in a language like Python, where none is just any old value that like any variable could have. None and sum are constructors of a particular type, option X. And if you have something of type option X, then you need the sum to be explicit to really be there. So the right thing to return here is a sum. Similarly, when you have something of type option X, you need to match on it to get the thing out to see what it is. Okay. Now Coq accepts it. Let's test. Okay, looks good. Now, it's open to debate whether or not this is going to be clearer than the version I'm about to write with a fun. Let's take a look. So I, just out of habit, whenever I'm writing a map or a filter, I'm going to tend to use a fun unless it's really complicated. So to me, that kind of determines some of what's going on there. But your mileage may vary. Right? You might have a different approach, and that's fine. I like this a lot, though. You'll notice the way that I laid it out, where now each argument is kind of getting its own block. I've noticed a lot of people laying things out like this, and I find it in this setting really easy to forget about the L and like not see it there. Whereas this layout is, I think, much clearer. You do, however, have to give it a new name. Okay, so in an attempt to show fix, I want to take this one step further. Maybe you don't want to use even b and then half, right? Because just as before we saw map and filter traversing the list twice, here we're kind of traversing the natural number twice, right? Even b has to count all the way down to 0 by 2s to see if a function is even. Okay, in a normal programming language, you just can detect it very easy by looking at the low bit, but whatever. And then this half n does that same traversal. So maybe we could do something a little bit clever here. Get our framing up. Okay. Okay, so what goes in here? So at this point, I want to write a recursive function. Here, let's just start with none and see if this type checks. Oh, it's complaining that wants a colon equals. Great. So now we have something that type checks but doesn't do anything. Oh, I didn't even test the right thing here. Oh my goodness, I've been doing the wrong test. Let's double check everything worked. Okay, we're fine. Okay, we're fine. So at this point, I've done a little trick here where I've gotten Coq to accept a well-typed solution that I know is wrong, right? Like I know it's not going to be right to return none every time. But what it does is it lets me like start running things earlier, which I know a lot of you would enjoy. Okay, how do we finish writing this program? Well, what we can do here is say, well, I want to do the halving and the even work at the same time. So let's find out. Match n with, okay, if it's 0, then we're just going to get some 0 out as the half. If it's s of 0, well, then we're going to get nothing out, right? Because we came down to 1 counting down by 2's. If it's s of n prime, then what do we want to do? Well, I'm not sure yet, so I'm going to write none. Cock accepts it. That's good. Okay, we're still getting nothing. Let's fix this case. So what do we want to do? We want to simultaneously check whether or not n prime is even. If n prime was even, we'll add 1, right, doing the work of the half function. And if it wasn't even, we'll return none. So match have even n prime with, well, if it's none, we got nothing out. If it's some n prime, then let's do s of n prime. Ah, thanks, Cock. It works. Okay, what is this function? I wrote it inline as a fix. What would it look like if I defined it separately? Well, we could have done this a bunch of different ways, right? Maybe I said something like this. Right, and then we could have called this have even elsewhere. We could have done a let fix inside of the function. Let's look at all these different versions. Ooh, 5 primes. It's a lot of primes. We're not yet up to Optimus Prime. We're getting there, though. So another way we could have done this would be to say let fix have even n be our trusty definition. Should be 6 primes. We're up to 6 primes now, right? All these are equivalent, right? Looking good. So all of these are good. I don't know which of these I like best. Honestly, I think have even is kind of a silly function, and maybe not like the worthwhile thing. Like I like maybe this version best. But maybe you want to go really hard on this. Maybe you want to go even harder than we've gone so far. Maybe you look at this and you say, well, wait a minute. I know a function that can kind of do this. That looks like option map. Right? Option map says, well, if it's a sum something, I'm going to apply some function, otherwise something else. So wait a minute, we could do even one better. Let's look. Let me show you a final bonus approach to have evens. That's right, ladies and gentlemen. We are going up to 7 primes. Option map S have even and prime. It works. So here, this option map is packaging up that like, oh, let me work with the maybe whatever. This is cool. I think this solution demonstrates some real understanding of what's going on. But like, which is easier to read? Which would you rather meet? Would you rather meet have even 7 primes or have evens 3 primes? Which one would you rather see in code? I look at this and I'm like, I know exactly what this function is doing. I look over here and like, okay, the name helps me. Like, all right, I believe you, but like, whew, this is a lot to keep track of. I mean, I appreciate the flex, right? Like you're doing a good job, but this is maybe not the clearest version of this function. I do hope it's been helpful for you to see a bunch of different versions of this function. I'm sorry this video has gone on so long, but pick and choose. This is really meant to be just sort of supplementary, getting you more comfortable with higher order functions. Okay, that's it for now. I'll have days 9 and 10 being posted soon as we get ready for days 7 and 8 this week. Talk to y'all soon.